Let's work on a slightly more complicated example, where we'll use a while statement to do something more interesting. Find the prime factorization of any positive integer. What is the prime factorization anyway? Well, each positive integer, n, has a set of prime factors, which are primes whose product is n. And it turns out there's just one unique way of writing a positive integer as a product of prime numbers, as long as you order them from least to greatest. 1 is kind of a funny case in that it technically doesn't have any prime factors at all, but let's not worry about that so much and focus on numbers bigger than 1, like 8 or 9 or 10 or 11 or 12. So here are their prime factorizations. How would you find the set of prime numbers that you multiply together to get some n for any n? Well, here's one approach. It's the one that I learned when I was a kid. Take n, find the smallest prime factor of n, divide by it, and do that again for the number that results by dividing n by this prime factor. So here's some number. Let's say we want to find the prime factorization for it. Well, we just start looking for primes that divide into it evenly. It's an even number, so 2 divides into it, leaving us with 429 left. What are the prime factors for this? Well, 2 doesn't divide evenly into this because it's an odd number, but 3 does. So 858 is 2 times 3. We found 2 first, then we found 3, and now we have to try to find a prime number that divides evenly into this. 2 doesn't work, 3 doesn't work, 5 doesn't work, 7 doesn't work, but 11 does. If you divide 143 by 11, you get 13. So first we found 2, then we found 3, then we found 11, and we'd have to find what prime number divides evenly into 13. Well, it turns out 13 is prime. So this approach of finding the smallest prime factor that divides into whatever we're working with to get some new number that we then find the prime factorization of is what's called an algorithm. It's a computational process. I could describe it in English, or I could describe it in code. So now that we have an approach, we can try to write the code that does this. And let's write it as a function of n. So let's describe what this does. Let's just print them out. Print the prime factors of n. And then start writing some examples. So the prime factors of 8 were 2 and 2 and 2 and 2. The prime factors of 9 are 3 and 3. The prime factors of 10. Well, now we have to pick the order. So how will we do 2 and 5? We might as well specify this. In increasing order would be one way to write it, but these aren't actually increasing, they're the same. So the point is that it never goes down. Sometimes it goes up, sometimes it stays the same. That's called non-decreasing order. Okay, if there's only one, we're supposed to print it out. The next interesting one was 12, which is 2 times 2 times 3. And then we did this tricky one, 858, which was 2 times 3 times 11 times 13. So now we have a bunch of examples. We can test our work. But how do we actually solve this problem? Well, we write down code that corresponds to the process that we came up with in the first place. As long as n is not 1, that means there's a prime factor for it. While n is greater than 1, I have to find the smallest prime number that divides evenly into n. How do I do that? Well, who knows? But let's not worry about how to do that. Let's just write down the fact that we have to. And we'll call the result k. Pretty soon I'm going to have to implement smallest prime factor. But for now, let's just assume that we could do it. If we could do it, then we would divide by it. I can use floor division because I know k evenly divides n. That's part of its definition. I also need to print k out. And I think that's all there is to it. To printing the prime factors of n is to find the smallest prime factor of whatever number I'm dealing with. So if this is 858, I'll find the smallest prime factor is 2. Then I'll divide by that to get 429. I'll print out the 2. And then I go back and do it again. Find the smallest prime factor of 429 is 3. Divide by that is 143. Print out the 3 and do it again. But I can't run this code until I define smallest prime factor. Well, the smallest prime factor, it turns out, is the same thing as the smallest factor, greater than 1. So I could just try dividing n by different values k, starting with 2, working my way up, till I find one that works. Return the smallest k greater than 1 that evenly divides n. So we'll start with 2. If it's the case that dividing n by k does not give me 0, that means k does not evenly divide n. Then I need a different k. And if I want to find the smallest one, well, I could start at 2 and then just work my way up. So this says try dividing by 2. If it doesn't work out, then add 1 to k. So then try dividing by 3. If that works out, then we return k. I don't return k in here because I only want to return after I've gone through this while statement long enough to find a k that evenly divides n. So it is important how you indent the return statement here. Indenting it at the same level as while means after while has repeated as many times as it's going to repeat, then return k. Whereas writing it here would say, the first time through, it's time to return. That's not when we want to return k. Okay, let's play around. What are the prime factors of 8? 2, 2, and 2. What about 858? 2, 3, and 11, and 13. So it does what it's supposed to do. In fact, we could run all the doc tests that we've written down so far and make sure that they all pass. So we've solved this problem, but we're not going to stop discussing it. 2 things I want to point out is that if you want to see how this is working, drawing an environment diagram is a good choice. So for example, I could copy my code, paste it in here, compute the prime factors of 12, and see what happens. There's 35 steps. That's not an overwhelming amount. The first 2 steps are just to define the functions. Then we call prime factors on 12, which immediately calls smallest prime factor. So it needs to find something that divides into 12. 2 does, and so it returns 2. So k is the smallest prime factor of 12. And then we change 12 to 6 by dividing by 2. And we print out the number 2. Now we go through this while statement again, finding the smallest prime factor for 6. That introduces another frame where n is 6, and the return value again is 2. So another 2 gets printed out, and now we're going to try to find the smallest prime factor of 3. So we call smallest prime factor on 3. That's another call to smallest prime factor, this time with n equals 3. Here we can see this loop do some work. K starts out at 2, but since 2 doesn't evenly divide 3, it changes k to 3. 3 does evenly divide 3, so we return 3, and watch what happens here. N is set to 1, because we divided 3 by 3. We're still not done, even though we've met the while condition, because we finished the body of the while statement, printing out 3, then check the while condition one more time. N is now 1, and so we're done. Prime factors returns none, but it's already done all the work it needs to do, printing out 2, 2, and 3. So if you want to see what's going on inside a program that you're writing, Python Tutor can be a good way to do it. But I'm still not done talking about this problem. I introduced this second function. Remember when I said I was writing this program, I didn't even know how to do this yet. Well, I did, but I was pretending I did. I just gave it a name and didn't worry about how to do it. That's a form of abstraction. That's functional abstraction. Now that we know how to do it, we could think about whether we needed another function at all. Could I have just kind of pasted this in here instead? Get the indentation right, and then I don't have to have 2 functions anymore. Well, it turns out this doesn't work, because return here was about returning back to the middle of the while statement in prime factors when we wrote it in the first place. Whereas now, if I call prime factors on 12, it tells me just the 2. This return statement isn't returning from this little block. It's returning from all of prime factors, meaning that we can't keep printing out the rest of the prime factors. Now, there is a way to get this to work, which is to get rid of this return. And now when we get the prime factors of 12, it behaves correctly. And I would say, this is not bad. This is a reasonable way of solving it. But there's enough going on here that I would think we'd need to rename k to the smallest prime or something like that, because it's pretty hard to just glance at the code and see what k is doing here. So now things have gotten a little bit more complicated because I had to change this name. Code still works, but now it's still kind of hard to read. Smallest prime is 2. It's not 2. It's eventually going to be that this name is bound to the smallest prime, but it's not at the beginning, which makes this program just a little bit harder to read than it would have been when we broke it up into 2 functions, one of which had the job of printing and executing that algorithm that we described at a high level earlier. Find the smallest prime and print it out. And the other one had the job of finding that smallest prime. So even with this name change, which helped a little bit, I still think this is a worse program than the one where we had 2. But it is an interesting program because it has a while statement within a while statement. And that is allowed in Python. As far as the interpreter is concerned, this program is just as good. So the moral of the story is there's more than one way to solve a problem, but often using functions and their names makes everything clearer than trying to fit everything into one long body of a program by nesting a while statement inside of another while statement.